it is a great pleasure to introduce now Sofia Celi from Cloudflare Inc. She's a cryptography engineer at Cloudflare, and besides that, she's been working on many interesting privacy projects, and I think she's going to tell us about OTR version 4. So, Sofia, the floor is yours.
Thank you so much for that really nice introduction, and I will go into share my screen and hopefully everything will work. Sure. Okay, hopefully you are seeing my screen properly. And yeah, thank you very much for inviting me. I was really happy to participate and show a little bit of the work that I have been doing for the past years now. So yeah, basically the name of the talk is The Devil is in the Detail, Designing and Implementing the fourth version of the off-the-record messaging protocol. And one of the things that I was wanting to talk prior to actually introducing the talk is to give everybody a little bit of a context. So what is basically this talk about? This talk is not only about what secure messaging is or what the off-the-record messaging protocol is, which is the protocol that I have been leading for some years now, but also I wanted to give a talk about what is the importance of secure messaging, and also if you're a software developer or an implementer that is trying to implement any protocol to give secure messaging, give you also a little bit of a context of what kind of drawbacks and what kind of difficulties we had when implementing these kind of protocols. So maybe hopefully you will not have the same problems. So just a little bit of some points that we have found out during our work that might be useful to anybody who's trying to implement something similar. So basically that's the context of the talk. And one of the things that I always love to start these kind of talks about is that it's a question that has always been posed to me, in the sense that there are many thoughts about, yes, we should probably communicate over the internet, because over the digital world, because that's one of the reasons why the digital world was created. But there's always a question, okay, sure, we can communicate over it, but why we need it to be, why we need it to be secure? Why? Because obviously we can communicate over the digital world by using any kind of plain text sending over the network, but why we needed it to be secure? And one of the things that I always like sharing when trying to answer this question is obviously some paragraphs from this really amazing paper from Philip Rockaway by the name of The Moral Character of Cryptographic Work. And he says that this is actually one of the most important problems that we can actually think about when thinking about computer science in general, but more specifically when we're thinking about cryptography. And one of the reasons he says, though, is that this is the most fundamental privacy problem in cryptography. Basically, how can parties communicate in such a way that nobody knows who said what? And as we will see during the execution of this talk, it's really difficult to answer the question of what exactly secure means in terms of secure messaging, what kind of actual privacy properties we want to provide when trying to give secure messaging, and if actually the protocols that exist out there actually fulfill the privacy properties that have been defined. So why is this important? Because right now we live in a world in which many different actors are trying to read the conversations that we're having, either to sell us some products or actually say, or actually know what kind of activities we do in our daily life. So that's really important that the communications remain secure. And we will see during the execution of the talk of why it's important when compared to the talks that we have in the non-digital world. But one of the things that we early found out when trying to sort in a way the secure messaging problem is that there was a lot of already protocols trying to provide secure messaging. There's of course many applications that you can install on your phone that try to provide you some kind of security, while at the same time trying to provide you some kind of privacy. Something that is really important when we were designing a certain protocol is that for us it was not only important to give certain security properties, but also to give certain privacy properties. And we follow the same school of thought of Philip Rockaway in the sense that there is not a secure protocol that we have seen that is only secure by default without giving privacy. For us, security is always an extension to giving privacy properties. So when we did this overview of the different protocols that exist out there, we realized that there's options, but we need options that actually work. There are many options of different protocols out there that exist on the papers, but we need things that have actually been implemented and actually people are using, because if not, a protocol has not really fulfilled the requirement of having users who actually communicate securely through it. We also need full specifications because, of course, there's really many lovely protocols out there, but many of them don't actually specify what kind of properties and what kind of algorithms are they using to the end users. So we actually need to give this all software full specifications that determine the different properties, cryptographic algorithms that they use. We also need protocols that correctly define the properties, limitations, and requirements that they have, because obviously a protocol should not aim to solve everything that is out there, because it will be really impossible. So the protocol should aim to actually say which exactly properties are they giving and which limitations, what are the limits that the protocol tries to give. We also need protocols that update existing definitions, and this is a common thing that we have in secure messaging sphere, in the sense that we sometimes use protocols that have been specified and have been defined years ago, decades ago, and of course the new cryptographic literature has now advanced in the sense that new properties have been better defined, new algorithms have been shown to be better than all algorithms. So we need to actually protocols who update existing definitions and algorithms rather than something that hasn't been touched for many years. We also need reviews and verifications, and this is something that we will talk almost by the end of the talk. But basically we need actually other people other than the protocol designers to look at certain secure messaging protocol and say, indeed, yes, this protocol gives the properties that they aiming to give, or no, they don't give. This is still something important. We need ideas from different places, and this is something that I'm really happy that right now the community is talking quite a lot, in the sense that we need ideas of what privacy definitions exist out there in the different regions of the world. Because sometimes we have a very Western idea of what privacy would mean for a region, when sometimes different regions of the world have a different idea of what privacy means for that region. So we need options that work for the different definitions that we have of certain properties in the world. And of course, we need implementations, because of course, end users need something they can use on their devices so they can securely communicate. That's sort of an overview of what we found out by doing an overview of the different secure messaging protocols that existed out there, and our conclusions that we had when implementing a new version of an already well-known secure messaging protocol. Okay, so just let's start with a little bit of properties, in the sense that when OGR was created, it was created because it tried to emulate what is called real-world conversations. So our first questions prior to actually creating a protocol for the digital world is actually looking at the non-digital conversations that we have every day and asking ourselves what they are really about and what kind of properties do they really give. So what are real-world conversations? Well, on a casual, real-world, non-digital conversation, we of course know who participates in this conversation, because you see the face of this person. Sometimes you even see an ID of the person you are talking to, because it might be a supermarket worker or someone who will show the ID and identity. You know what is being said, of course, because you are listening to the conversation in real time, so you know exactly what's being said. You know who is listening to it, because unless you're recording it through video or through audio, you know that only the two parties into this conversation are the actually ones listening in. Of course, this has changed during the years. There's many countries in which it's legal to record a conversation that you're having with a person without the consent of the participants involved. In many countries, it's illegal, but it still happens. Like, for example, there's many countries where this is illegal, but of course, there's some cameras always recording over the city certain conversations you're having, or even the images of you having the conversation with someone. But in theory, through the legality, it should be illegal in certain countries. And of course, you know how long it lasts, because of course, if unless recorded, you know that because if unless recorded, you know, of course, that the conversation will end when you say bye, when you say ciao, when you say see you tomorrow. then the conversation will end. Unless, of course, it has been recorded through video and audio, because if it has been recorded through video or audio, then you don't know when this tape will be deleted. You don't know when if this conversation was uploaded to a certain service. You don't know when this will be taken down, etc. So just by this, we of course already know certain properties that these real-world conversations are trying to give us and that they have. Of course, you always know who participates in this conversation. Of course, you know who is listening to it, and you can choose who listens to the conversations. You know how long it lasts, and of course, you can choose also how long it lasts. And you know something about the identity of whom you are communicating with, in the sense that you either know how this person looks, or if you're talking with someone who has an ID, you already know the name of this person, etc. So you know a little bit of the identity. Sometimes you preserve anonymity in the sense that you don't know exactly the name of this person, or an identity, you don't know the identity of this person, but at least you know how they look like or how their voice sounds like. Okay, so this is a little bit of an overview what you have already in the real world conversations, and from this, obviously, certain different cryptographers out there look at this problem and look at these different properties that real world conversations were trying to give, and try to emulate and give the same properties to non-digital conversations. So in the beginning, there was two very big protocols that were used to securely communicate over digital communication, over the digital world. And these two protocols are obviously PGP, and the other protocol that exists to securely communicate is obviously TLS. But during that time, three cryptographers by the name of Ian Goldberg, Nikita Borisov, and Eric Brewer look at these protocols and say that they were not enough to give the different properties that real world non-digital conversations have. And the reason why they say that they were not enough is because many of them didn't fulfill all of the properties that we have in the non-digital conversations. Because if we want to give a certain secure communication and private communication to digital user, we should aim to mimic what the properties of real-world non-digital conversations give. So obviously, PGP don't give you fulfill all the requirements of real-world conversations, because, for example, you always have a record of PGP. You always have a proof of authorship with PGP, in the sense that if, for example, you send an email to another party that is PGP encrypted and authenticated, then this is an evidence that can be used against you of that you indeed author certain message, and that you author the message, and that you sent indeed this message. And this is in a way a proof of authorship. And this is something that obviously you don't have in the non-digital world, because when you say something in a conversation, let's say you say something like, I really hate this person, you said it to a colleague or something like that, and then this colleague runs into the person you say you hate and says, oh yeah, Sophie said that she really hates you. Obviously, I can always deny having said so and say like, no, I didn't say so. I was not the person having that conversation with this other person. I can always deny it. But in the digital world, you cannot send it. If you indeed send an email with PGP that is authenticated, then this actually evidence that you indeed said what you intended to say, and that you cannot deny later. Why is this important for conversations in general? It's because humans in general are a little bit of an emotional being. So sometimes we say things that we later regret, or some things that we like to not really have said it because we're emotional at the time. So it's always good to have the ability to deny having said something because in a way it could incriminate you. It's more important even to people who are working with high-risk activities, for example, journalists or searchers that are trying to leak something, because obviously they don't want to create certain proof of authorship that later is going to be used against them. So if you're someone that's working at a big company and you're trying to release a secret that you think that the public might know because it violates certain human rights, it violates certain rights that we have, and you go to a journalist and say, hey, I want this to be leaked, but please keep my identity concealed, and please use the off-the-record property that journalists usually use. Obviously, the journalist is also bounded to keep your identity conceal. So if at some point there's someone thinking that indeed it was you, the one who leaked certain secret, then you can always deny having the one who says so. And there's always not a proof of authorship that you indeed said so. Okay. So that's what the different cryptographers look at the different protocols and realize that they were not enough to actually give you the same properties that real world conversations actually have. Okay, so they say, okay, this is not enough, but let's start trying to create a protocol that actually gives the properties that we want to give. They indeed created this protocol, but first they say, okay, let's start with certain properties that we actually want to give the end user so they can have secure and private conversations. So the first property that I looked at is this property that is called forward secrecy, that basically means that you will use unique keys for each message that you send during a conversation, which means that any kind of messages that you sent in the past prior to the message that you're currently sending are locked in the past, in the sense that they cannot be decrypted, even if an adversary manages to get one of the keys for the message that you're currently sending. So basically this means that even if you send right now a message and this key, which is used to encrypt this message, gets leaked to an adversary, any messages that were sent in the past remain confidential and remain secure because each message was encrypted with a different key. This is something in which also PGP or the protocols for don't actually give, in the sense that with PGP, for example, you are not really using one key per message, so this property will not also be used with certain protocols. And how this was actually achieved, usually in prior versions of the off-the-record messaging protocols and other protocols, basically this was achieved by using this algorithm, which is basically the difficult monkey exchange. I'm sure most people here are familiar, but basically what the aim was that each time that you send a message, you will add new randomness, you will create new keys, so the message will be encrypted with a different key. Now, what is the problem of this? The problem of this is that, of course, you will have to be generating keys every time that you send a message, and also advertising this key that you are indeed generating new keys to the participant in the conversation. And this has problems for efficiency because generating a key per each message can be costly for anybody executing it. Okay, so hold that thought on why is this what that was problematic, because we will come back to that in a moment. But at the same time, first I wanted to talk to you about the parallel property that forward secrecy has. And the parallel property is a property that's called post-compromise security. Forward secrecy was about past messages. The past messages remain confidential and secure, even if an attacker manages to figure out one of the keys from one of the messages. Post-compromise security is about the future. So it says that future messages that you're going to be sent also remain confidential and secret, even if an attacker manages to get hold of one of the keys used. The full property that right now I'm currently talking about is actually called backward secrecy, but right now in practice we don't have backward secrecy actually implemented in any of the protocols that exist out there. We have post-compromise security, which is sort of a weaker property that compared to backward secrecy, in the sense that post-compromise security says that, of course, future messages are going to be confidential and going to remain secure, but only through a certain time frame. So what happens in the different protocols that we have out there is that for example, if you send a message with a unique key, then probably the subsequent 5 messages that you're going to send are not going to remain confidential or secret, because if an adversary gets hold of that key of the message that you're currently using, then 5 more messages that you send probably can be decrypted by this key that was used by the current message. But then once the 5 messages are sent, the new randomness, new keys will be generated, and then the subsequent messages will be indeed protected. So this means that you always have a time frame. In this case of the example that I'm giving is 5 messages. It's not perfect, that it will mean that every message that you will send will indeed remain confidential and secret, but it means that you will have a time frame in which the messages might be compromised, but then new randomness and new keys will be generated. Okay, so how is this actually achieved in practice by the different protocols that we have out there? This, for example, in the Signal protocol, this is achieved by the usage of the double ratchet algorithm. The two properties that I have talked about, forward secrecy and post-compromise security, are actually achieved by the usage of the double ratchet algorithm. How this algorithm works is basically that each time that you send a message to the other party, you actually generate new keys. But if you keep sending messages in that ratchet, for example, you send to the other party, hi, and that's one message that gets encrypted with a unique key. Then you send, how are you? That's a new message that also gets encrypted with a key derived from the previous one. Those messages are encrypted with only new randomness, with the same randomness. But once you receive a message from the other party saying, hi, how are you? Then new keys will be generated. So instead of generating the Diffie-Hellman keys each time that you send a unique message, what you do is that you generate new randomness every time that you have received a message from the other party, then you start new randomness, new keys again. But when prior to actually receiving a message from the other party, what happens is that you will just not generate new keys, but rather create keys by deriving new keys from the previous one. So as you see, this is a sort of a ping-pong mechanism in the sense that you have to wait for the other party to send you a message so you can actually create new randomness and create new keys. It's a ping-pong in the sense that one person speaks, the other person speaks, and then new randomness is created. But if you are the one only sending messages forever without receiving a message from the other party, then you will not actually add new randomness or new keys to the conversation. Of course, what this gives us is what I said, that it gives you post-compromise in the sense of giving you a time frame. What is actually referred in certain papers as channel healing, in the sense that, of course, during a time frame, you will not, your future messages will not be secure, but once new randomness is added, then again, they will be secure again. This is really interesting when talking about these two properties, because they are closely related to what the Signal protocol aims to give, and it actually indeed gives. And the Signal protocol has created very lovely in research and investigation about these different properties as a statistic. But something that is sort of a critique to our community is that indeed during many times the Signal protocol was actually implemented and using without having a good idea if the properties who were actually claiming to be given by the Signal protocol were actually given. It took like 7 years or something like that to actually for researchers to look at the Signal protocol and actually indeed say, yes, indeed this protocol is actually given the properties that they claiming to be given. And it's really interesting if you want to read about the actual properties that Signal is giving and some other properties that it's indeed given. You can read a paper by Alwyn Coretti and others that was published on Eurocrypt 2018, if I'm not wrong. And they actually did a verification that the Signal protocol was indeed given the properties that they claimed that they were given. And they also found out that they were given two other properties, which is immediate decryption, in the sense that at any time that you receive a message by using the Signal protocol, it gets immediately decrypted. You don't need to wait until a key gets advertised or wait until certain messages arrive. No, it gets immediately decrypted. And it's also message loss resilience, in the sense that even if you're putting the Signal protocol on top of a network that does network package reordering or it has package loss, it will still work, because it doesn't matter the order that you're sending, because it will still be able to decrypt the messages. So really interesting paper if you want to check it out. And this was sort of more what I talked about, was more of the secure properties that exist out there that we want to give in secure communications. Now, for the privacy properties, of course, we have different ones. We want messages to be authenticated. Sometimes we want them to be anonymous. But specifically on the OTR protocol and certain other protocols that exist out there that are trying to give secure messaging, they want them to be deniable. And the type of deniability that they give is actually something that has been quite debated lately in the cryptographic and security privacy community, because sometimes it's not actually well known what kind of deniability they're actually giving. Of course, deniability per se is a property that has had a lot of debate. But for the moment, I'm just going to talk about the different types that exist out there. So I already defined a little bit about deniability was, but basically the ability of deniability is that someone who is trying to say that indeed you author a message during a conversation should be unable to distinguish between the real messages and fake messages. And there's different types of this kind of deniability. You have online, offline, message, and participation. So let's start with the easier one, which are the ones who are message and participation. Message deniability says that you should be able to deny having said a specific message in a conversation. And participation deniability means that you will be able to deny having participated in the conversation at all. And now for the most interesting ones, which is online deniability and offline deniability. And I'm taking the definitions from a really interesting paper that I can also read by Nick Unger and Ian Goldberg that is called Improving Strongly Deniable Authenticated Key Exchange for Secure Messages. It's really nice paper published on PETS 2018, I guess. I'm not sure, but you can check it out. And basically what they say is that offline deniability is the property by which a transcript of a protocol should provide no evidence of actually a conversation taking place after the protocol has been run. So it is always offline. After the fact that a conversation took place, there should be no evidence that actually indeed this conversation took place. And online deniability means that there's an outsider that is trying to obtain evidence should not be able to obtain evidence, even if it's interactively colluding with the conversation. What this means is that online deniability preserves deniability even during the execution of the conversation. So even if you have someone trying to indeed prove that you are in a conversation while the conversation is happening, deniability should preserve. There should be no evidence that indeed this conversation is taking place. Yes, so in practice, how this actually is achieved in the first kind of property that I was talking about, which is offline deniability, means that after the conversation happens, anybody should be able to forge a transcript of the conversation. So an adversary will not be able to distinguish between the real transcript and the forged transcript, because the protocol gives you the ability to create forge of the transcript. Online deniability, on the other hand, as I said, is during the execution of the actual protocol, and this is a property that's actually more difficult to achieve and only has been shown to actually be fully achieved on the non-interactive version of the OTR version 4 protocol, because, for example, the Signal protocol actually don't give you deniability. I think I have a question in the chat or something. Okay, sorry, I'm just briefly going to check this. Okay, yeah, sorry. Yes. So it has been shown that indeed the Signal protocol doesn't actually give you online deniability because it's much more difficult to achieve. If you want to achieve online deniability, then this property has to be really ingrained in the design of your protocol. Because, for example, in the usage of OTR in version 4, it's actually achieved by using a deniable authenticated key exchange, which means that if, at the time that you're sending your long-term key and generating your first keys to be used to encrypting the different communications that you're going to send during the conversation, at that time that process has to be deniable, because if it's not, then the protocol will not be deniable, online deniable at all. So in the OTR version 4, this is achieved through the usage of this primitive that is called a DAC and through the usage of ring signatures. And you can check the protocol specification itself, so if you want to check how the algorithm actually looks like. Of course, in offline deniability, as I said, you can be able to forge transcript, and this is achieved through different ways. Sometimes by revealing the keys. Most of the times is achieved by revealing the keys. And of course, in online deniability is by the usage of ring signatures. And as I said, it has been proven by this paper that you can see in this slide that actually on the Signal protocol online deniability is not actually achieved, because if you use something like as remote attestation and a trust environment, you can actually prove that during the execution of the Signal protocol, you can actually prove the authorship of messages of the parties that you are communicating with. And you can check for the details in this paper. Now, another sort of property that usually secure messaging protocols want to also give, and it's sort of a property, is verification, in the sense that you actually want to verify that indeed the keys that have been used during the conversation to authenticate actually belong to the party you think you are communicating with. And in many cases, this is still an open problem, and I invite the audience to actually think about it more properly. Because right now, the way that you do verification is by either using, for example, fingerprint checking, or by using a protocol that is called the Socialist Millionaire Protocol. Another Signal also has safety numbers options. It has been shown in some recent usability studies that actually people don't know why verification is needed, and specifically in the Signal application and implementation, most of the users of it don't actually know what it is about, and they never actually use it. So it might be actually an interesting research to actually look at what would be a proper way to actually verify the keys of participants in a conversation, and what kind of usability actually what kind of usability properties actually the different ways that we right now have to verify actually give. So that will be something interesting to look upon. Okay, so that's basically the properties that OTR in general wanted to give in general from since its inception, since version 1 until the version 4 right now. It wanted to give forward secrecy, wanted to give compromise security, and it wanted to give certain flavor of deniability. What we did when we were doing the version 4, that I present a little bit later of this protocol, is that we also looked at the state of the art of the different protocols that exist out there to check if indeed they give the different properties that we mapped were important to have in the secure messaging and privacy communication protocols. And what we found out is that most of them don't actually give in fullness the different properties that we mapped, in the sense that, for example, in the version 3 of OTR, obviously there's not at all online deniability, there's weak forward secrecy, and the same on the different kind of protocols. And what we aim in the version 4 of OTR was to give almost in its fullness the different properties that we mapped. Of course, when we have limitability in the version 4 OTR, for example, we only have weak online deniability for non-interactive participants that are using this protocol. So yeah, you can check a little bit later if you want. I can also talk during the questions about why specifically some of these protocols don't actually give in fullness all of these properties. Of course, in the state of the art, we have right now a lot of really interesting and really good messaging applications that aim to give secure and private conversations out there. A Signal, Wire, Riot, that's now Co-Element, Omimo, WhatsApp. In the terms of group chat, we also have right now the effort from IETF, the message layer security, the MLS. But what we have found out is in general that there's still some work needed to be done. There are great applications and protocols that are pushing forward the research, but there's still obviously some things to be done in terms of, for example, actual usability of the people who are using it. And in terms of, when I say usability, it's not only about the user experience or the UI or how the UI looks like, but actually about how actually users use it. So one of the things that we found out when looking at these different applications is that, of course, some of them, for example, give a desktop version of their clients. But what we have found out is that people are moving away from it, and they are actually looking much more into only having a mobile applications of these kind of protocols. What we also found out is that people are moving away from this protocol for messaging that's called XMPP, and they are moving into something that is more sort of centralized in the sense of some of these protocols. But still, there's still some need for actually having good decentralized solutions for these kind of protocols, in the sense that, for example, there are many users who have reported who actually want to have a way to, for example, communicate over signal, but by using wire at the same time and using a decentralized ways in which these different protocols can talk to each other. Why do they want this? Is because generally we have too many apps to install. I have in my phone like 10 different apps of the different secure messaging protocols that I have had to install. And obviously for a user it's not great, because you will use one app for one thing, you will use another app for one thing. If you install different apps in your mobile phone, obviously these apps will have different kinds of vulnerabilities. If you install more of them, then you will maybe installing more vulnerabilities into your phone of the different apps. So it's not great to have too many apps to install. So it would be great if we have a solution in which the different protocols can talk to each other. I really like in this way the message layer and security efforts that have been happening, in the sense that it's trying to create something that can be used, that can interoperate between different implementations of that protocol. So it would be great to actually have. Obviously, on some of this protocol, on some of this application, there's not really a clear understanding which kind of privacy and security properties are given. As I said on some previous slides, it took some years to actually for the researchers and academics to look at the Signal protocol and actually say, yes, indeed, this protocol is giving us the properties that it's claiming to be giving us, but there's still some need for the different other protocols to actually take the same step as it was taking from Signal, to actually take the protocol and specification and verify it and review it and say, yes, indeed, this protocol is giving the properties that it's claiming to give. And still an open problem that exists out there is that there's no good synchronization between devices. Sorry for the noise. Yes, that there's no good synchronization between devices, in the sense that the multi-device problems remains an open problem, because there's not a good way to actually properly synchronize between devices. There's some steps that have been given by the different protocols, specifically by Signal and Wire, but of course the synchronicity of the devices is only through the desktop client and to the mobile client. Remains to be seen what will happen if indeed this becomes decentralized. What will happen if you, for example, try to have a multi-device between different protocols. There's no mapping of the security privacy properties into the user interface. For example, let's say that you want to give in your protocol for web secrecy. Of course, you can have something in your protocol as disappearing messages that will actually give you from the user interface actually for web secrecy, in the sense that let's say that an adversary takes your phone. Obviously, this protocol gives you forward secrecy, but if an adversary takes your phone and manages to know your password and decrypt and unlock your phone, then this person will be able to see all of the conversations that you have had with the different contacts that you have. And does this actually give you forward secrecy? Remains to an open question, because the messages are still out there, even though they were encrypted and decrypted with a unique key. So some good steps that have been taken to actually map these properties into their user interface is, of course, the idea of disappearing messages that have been pushed by Signal and Wire. Wire even has, like, for example, the option to delete individual messages from your device and from the other person's device, which can be a great thing as well. Something that remains an open question is actually deniability in the user interface. So, for example, there are many of these protocols who claim to have deniability, but for end users, they don't actually know, not even know what deniability is about or how that actually works. So it will be actually good to actually have some kind of explanation of this in the actual user interface. Okay, so this was basically some little research that we did about the state of the art of the different protocols that exist out there. Now, after doing this kind of research and after doing this kind of investigation, what we wanted was to create a version 4 of the off-the-record messaging protocol. And what we wanted, obviously, is that we wanted the different properties that I have already spoken about. We wanted deniability. We wanted all of the flavors of deniability, participation message, online and offline. We wanted, obviously, forward secrecy and post-compromise security. We wanted to increase the security level, and this ties with something that I spoke earlier in this talk, that we wanted to update the different cryptographic primitives, so we don't use primitives that have been shown to have vulnerabilities. And this overall increased the security level of the protocol. We also wanted some additional protection against transcript decryption and against elliptic curve compromise. So right now in the version 4 of the protocol, we're using elliptic curves, but we're also using classic traditional Diffie-Hellman. because in case that they get compromised. And of course, we wanted elliptic curves because elliptic curves are cool, and also because they are much more efficient when comparing them with traditional DV helmet. We also wanted to actually give a protocol that it's more ingrained and more in tune with the new communication model that exists out there. When OTR was first designed, it was designed for a network model that was always expected to give packages in order. But now, of course, with the properties the signal has been given us of message resilience, obviously we wanted a protocol that should be able to also handle out of order delivery of messages. We wanted also online and offline conversations, and this is something that OTR on its previous versions didn't actually have, because it only worked for online conversations, which means that it only worked when the parties were actually online. But obviously in the new communication model and the new applications that we have, we also want to send messages when we don't know if parties are online. So we also wanted to give offline conversations. We also wanted to give different modes, because this is something that ties together to the different users that use the different messaging protocol that you're using. Some users obviously are going to have a higher thread model than other users. Obviously, a journalist that is talking to different sources will have a different thread model than the normal users. So we wanted to give also the option to have different modes in which the protocol can be implemented depending on the type of users that was going to use the protocol. And we don't want to trust server, and this is a critique that certain secure messaging applications that exist out there have, in the sense that the server is sort of proprietary or sort of comes from the same company in which the protocol has been developed. So there's not actually an idea of what actually this server does. And obviously you as a user have to trust that the server is actually indeed doing and storing in an appropriate way your information. So in the OTR version 4, we didn't want to do that. We wouldn't wanted that you use whatever server you have because you actually trust it. And of course, a question that we always have when talking about a new version of our protocol is, do we need this new version? Do we actually need to have this new version? I hope at this talk that you actually seen that it's important to have new versions, in the sense that it's important to give new cryptographic primitives, but also to update the existing definitions of properties that exist out there. Of course, as I said, one of the most interesting things when designing a protocol is that obviously the protocol will not solve all of the issues in one go, but it will always have some limitations and some issues that it was given. So in the version 4 of OTR, we actually wanted to properly say what limitations and what issues exist out there in our protocol. So the limitations, of course, is that OTR is not metadata resilience, is not metadata protected. This is still an open question that we will talk a little bit more in a moment, in the sense that, for example, if a protocol gives anonymity, but it also gives deniability, there has not been research actually, not much research actually today, to actually know if the deniability properties on top of an anonymity network will actually work, or if they will cancel themselves out. There's still work to be done in that area. Of course, OTR is aiming to give some kind of post-quantum protection by the usage of an outer layer of a traditional DV helmet, but we're not using any kind of post-quantum algorithm because we're still waiting for the result of the NIST competition to actually say, yes, indeed, this post-quantum algorithm is the one that we should use. We have an idea right now what kind of post-quantum algorithm we might use, but we're still waiting for the result of the competition. And of course, OTR does not give group chat support because the deniability properties that I have exposed don't really work in a group chat setting, or there still needs to be research done in the terms of actually defining deniability for a group chat setting. There's some efforts, again, from the message layering security protocol from IETF, but it still remains to be seen what the outcome of that is. Of course, there's still some open problems that are still need to be tackled by OTR and by other protocols about the synchronization of multi-device problems that I briefly talked a little bit in some past slides. Of course, that how to properly map the different properties, security and privacy properties that are given into the user interface. Like, for example, this what I talk about of the disappearing messages or no history options that sometimes are given by certain protocols. Of course, there's still research to be done about the impact of the top properties on the underlying protocol. Like, for example, what I say, what's the impact of deniability if your underlying network gives you anonymity? What's the impact of deniability if your underlying network gives you some TLS with authentication of some way? It still needs to be done some research around that. There's still an open question about if there can be a mode for deniability. There's some conversations that have been having at some points, in the sense that, for example, can it be that a protocol only give you offline deniability in one mode, but online deniability in one other mode? How they will interact? This still is an open question. And of course, the questions that I always pose to people who are trying to design new secure privacy protocols is that if you actually need another new protocol, or you just need to update a protocol that exists out there. I usually like more the answer of let's just updating a protocol that exists out there and people are using it, rather than to create a new app, a new protocol, because that will mean for a user to actually create and install a new application into whatever device they have. Okay, and as I said at the beginning, this talk was only not to was aimed not only to give some answers from a protocol design perspective, but also from an implementation itself. So when you are implementing your secure messaging protocol, of course, you have to always think about which language you're going to choose, which library you're going to use. And these are really important questions in the sense, if you're going to use a language that is memory safe, if you're going to use a language that is threading safe, if you're going to use a language that is very usable for whomever is going to take your protocol and then put it into their application. So these are open questions. Of course, in the OTR version 4, we chose to go from Z, but we're currently developing also a library on Golang and probably on Rust as well. Of course, there's still some open questions in the sense of how to correctly store, delete, change keys. And this is the question in the sense that there's still also needs to be some research done in this to the other protocols that we have already installed in our devices to see how they actually store, how they actually delete the different keys that are being used in the protocol. Of course, there's a problem when implementing how actually you manage keys in the same sense of how to store, delete, or change them. Of course, the same problem of should service be trusted. And if you don't trust the service and you want the users to give the possibility to the users to use whatever server they want to use, of course, how this will actually look from an implementation point of view is an important question to ask yourself. And something, of course, that is always important is to actually have your code audited in the sense of actually writing your protocol and then having some security people actually look at it and see if it's indeed safe to use from a memory perspective, from a threading perspective, from a sanitation perspective, etc., etc. And of course, it's always important to, prior to actually implementing the protocol itself in whatever language, to actually think first of how the user interface will look like, because usability and user interface and user experience should come first prior to actually the implementation of the protocol itself. Okay, and with that, I come with my talk. I will take any question, but this is a list of the different people who have been involved in the design of the OTR protocol. It's not an extensive list, it's not an exhaustive list in the sense that there's more people involved, but this is the ones that fit the slide. Here are the repos if you want to check them out. And of course, some references. Questions we have on RSC. And thank you very much.
Just a second, we're trying to activate also the video. Yes. Okay. Hi. So while we're waiting for questions in the chat or in the Q&A section, one question, you discussed a lot about deniability, and I understand that this is something that most of the other messaging services are not using, and I understand why it's important. But do you know of any real-life users, meaning something like who are really in the need of that, and are there any success stories for OTR over the years you can share with us?
Yes. that is usually the question about deniability. So, about one of the things that is always talked when talking about deniability is what is usability in actual court cases. And if indeed there has been a court case in which deniability has been used, there has been known. Because one of the things that happen with court cases is that obviously plain text is used as evidence that indeed you were part of a conversation. In some jurisdiction, plain text evidence is still thought of as sufficient evidence to be used in a court case to say that indeed you authored something in a conversation. Now, that is one of the things that I have seen why it's not used in court cases. The first thing that we will have to do in court cases is first make them understand that in order for a message to be actually authored by you, then you have to have the digital signature attached to that message or some kind of evidence that indeed you author this message. And then on top of that, you will have to put deniability. So the first thing, the first thing that we will have to convince courts is actually to say that indeed we need some kind of authentication mechanisms of a digital communications. And then on top of that, you will have to make the case for deniability. So in this sense, it has not really been used. Now, I know that in the specific case of OTR was used during some conversations between Assange and supposedly between Chelsea Manning, and it still has not been proven that indeed it was her during that conversation because indeed she was using OTR. And indeed the conversations remain secure because they were using OTR. So you can put that case if you want. In a way, I don't like always giving the example of court cases because from my experience, when also working with, for example, intimate partner violence or when sexual assault, it has been proven to me that most of the time court cases don't actually care sometimes about the different properties or the different claims of victims. So it's really difficult to actually talk about how court cases actually work. Now, something that also happened, and one of the reasons why people are also talking about a case for deniability is in the sense, for example, of the use of DKIM. For example, during the leakage of the Democratic Party emails, it was actually proven that it was indeed, I think it was Hillary. Sorry, I'm not that intimately tied with the different US politics. But yeah, I think it was shown that it was indeed her, the one who was offering messages. So there was this case that if she was using some kind of other protocol that wasn't giving that was indeed giving deniability, she would have not been accused of certain emails that were supposedly sent by her. So yeah, there's that case. I have seen this in practice actually being needed in the sense that I have indeed seen in practice journalists wanting to have some kind of deniability properties because there's this concept in journalism from which OTR takes the name of being off the record that sources usually ask for, of being off the record. But in most of the cases when a source is talking with a journalist, they will use certain messaging application and they will not be indeed, they will not actually know if the conversation is actually deniable. When this will conversation leak, if it leaks, if it will show actually the identity of this participant. So there's the need in that part. Yes.
But there's the deniability of actually the contents of the conversation, and there's the deniability of actually holding the conversation.
Yeah.
And I think these two are very different from what people expect. I think that, can you please try and elaborate? Yeah. Distinguish between the two?
Yes. So of course you can have deniability of participating in the conversation itself, meaning that you can always say, let's say, yeah, I deny having participated in this conversation at all, and some protocols give that. But at the same time, this conversation cannot like maybe give you message deniability in the sense that maybe by inferring certain information on the message that you send, you can still infer that indeed you offer this message, but you cannot infer that you participated into the whole conversation. Because I don't know, for example, in one message you say, hi, my name is Sofia, then of course that message might not be deniable, but the whole conversation itself, you can deny having participated in it. Now, and then message deniability means that of course only one message you will deny. Like, for example, specifically this message that is important for me, I would say I can deny, but indeed I cannot deny that indeed I participated in the conversation itself. So yeah, these are two a little bit difficult, and in the new research that I have been reading, for example, there's not much focus anymore on actually thinking about message and participation, because the aim is to give those two properties by default, but more to the aim of actually thinking about offline and online deniability, by giving offline deniability in the sense of message and participation, and online deniability in the sense of message and participation as well.
So even in deniability, we're moving from encrypting end-to-end to defining the metadata, or vice versa.
Yes, so that's an interesting area of research that still needs to be done, because, for example, what I said is like, we don't know how, for example, deniability properties will work on top of anonymity, because obviously in deniability, you need to be assured of the identity of the other person. That's like the key properties. You want to have a conversation with whom you're thinking you're having a conversation. But over anonymity network, it's still not clear if this property of actually knowing that you're indeed talking to the correct person, but this proof is not going to be transferable to anybody else but the participant in the conversation, will work on something as an anonymity network. So there's still research to be done about that.
Thank you very much. And we now have a question from Paris Campaner. The first one is, which tasks would be in the top 3 priority list with development of OTR version 4? I have a feeling this is a requested question by you.
Yes. 3 priority list, the development. So right now the protocol is basically done. Like, for example, we don't need that. And right now we have just finished doing the user interface and usability research for OTR version 4. So the actual priority will be to actually take the UI that we have defined and actually implement it. We're doing an implementation to an XMPP chat that is called Chat Secure. So probably that will be also what is needed. Something that we have thought in the past is maybe also giving our own application of OTR, our own app, but it remains to be seen if it's a good idea or not. And the other one is, which tasks will be in the top 3 priority list with respect to the open challenges related to the improving of OTR? Okay, so there's still the challenge of actually, for example, giving a good synchronization to the multi-device problem. We have a proposal for a solution for this, but it still remains to be seen if it actually works in practice. Now, something else that is still needed is a formal verification. Yes, that as well. And this is something that probably we're going to start in November to actually, with some researchers, to actually do the formal verification of the protocol. Refining new definitions, no, that has already been done. Coupling with network anonymity, that is something that we have not actually thought about, because I have just studied some research about actually how deniability works on top of anonymity 1 month ago. So it will still take like at least 6 months to 9 months to finish that research, but it wasn't the aim of OTR at any level to actually give anonymity. It's not one of the aims of the protocol. But of course, there is still now some good protocols that are, from messaging, that are trying to give anonymity. Like, for example, there is protocol that's called Technion, that's trying to give anonymity properties. It would be really nice to see, for example, on top of that, you can put something like OTR. But that it's not right now a priority, because it really needs lots of research at the moment.
So thank you very much for joining us today.
Thank you.
And for all the participants, we're going to take 40 minutes break and reconvene at 12:40 Israel time, which is 5:40 a.m. if you happen to be in the East Coast. And I'm not going to embarrass myself by computing to Australia or India or any of these time zones. So see you in 40 minutes, everyone. Thank you, Sofia.